We all know that energy can't be created or destroyed, but only transformed. We can convert energy from one form to another to supply our final use with the most appropriate one. So, what is energy efficiency? In a few words, the use of less energy to perform the same task or produce the same result. For example, a car that uses less fuel than another one to reach the same place. Primary energy is the form of energy available in the environment before any conversion. It is the first link in the chain. For example, primary energy embedded in a fuel stock or in solar radiation is converted to thermal energy for heating a space or producing domestic hot water. Non-renewable primary energies are fossil fuels or mineral fuels. Renewable primary energies are solar energy, wind, biomass, etc. Efficient conversions of non-renewable primary energies allow for a reduction of emissions and fuel costs. Efficient conversions of renewable primary energies will reduce the size of plants, investments, and operating costs. While the first law of thermodynamics allows us to make a balance between the energy quantities during a transformation, the second law enables us to account for its quality, provided that every real transformation causes a degradation of it. Focusing on the task of HVAC systems, we'll now discuss some typical energy efficiency techniques and technologies for heating and cooling purposes. Heat pumps, cogeneration, trigeneration, and district heating and cooling, heat recovery in mechanical ventilation, efficient combustion with latent heat recovery in condensing boilers. A heat pump is a refrigeration machine where the cold sink is the environment and the heat recipient is the space to be heated or hot water tank. Basically, it takes the heat from the coldest system and pumps it to the warm one. No combustion occurs, so the heat is transferred with a small gap of temperatures. The smaller the gap, the higher the heat pump efficiency. In cold and moderate climates, air temperature in winter could be too low to achieve efficient conversion, so it can be smart to extract it from the ground or natural water bodies, reservoirs. Thanks to their moderate swing of temperatures during the year, better efficiencies are possible. Same considerations can be made when the cycle runs in reverse mode and the machine works as a refrigerator of the indoor space. As Carnot says, the smaller the temperature gap, the higher the refrigerator efficiency. Even in this case, water reservoirs or ground achieve a minor delta T. Cogeneration systems are power generators made to exploit heat not converted into electricity to support heat demand of close users. They are fed by oil, natural gas, or biomass, and waste heat is dramatically reduced while a great part of it is exploited for a final use. Trigeneration systems also use heat to feed a regeneration cycle, supporting a final use of space cooling or industrial refrigeration. In this case, we need a refrigeration device that can be activated with such recovered heat. Absorption machines are the most spread heat-driven refrigeration machines. The energy required to activate the process is not in the form of mechanical work as in the vapor compression chillers, but in the form of heat. It can be provided by solar thermal plants. In general, the higher the temperature of the heat source, the higher the efficiency of the cycle. Dedicated district heating and cooling networks can be built to distribute heat or cold to several users. They are usually connected to a cogeneration or three-generation system or other heat sources, such as large solar thermal plants. Last generation DHC networks are designed to distribute heat at very low temperatures, below 30 degrees Celsius. Users may increase the temperature of the fluid using heat pumps. At the same time, they are allowed to discharge waste heat into the network, making it available for the community. Proceeding in our discussion of typical energy efficiency techniques and technologies, we need to consider air renovation as a crucial task to grant good indoor air quality. Each unit of mass of fresh air supplied to a room takes the place of the same amount of exhaust air. This is discharged to the outdoor environment. Exhaust air, while generally polluted, already has the temperature and the humidity of the controlled space. On the other hand, fresh air has the condition of the outside environment and needs to be heated, cooled, and humidified or dehumidified before being supplied. An efficient ventilation system can recover part of this wasted energy through two kinds of recuperators. We can have sensible heat exchangers, which are able to reduce the temperature gap between the two air streams, or enthalpy exchangers. We can also transfer humidity. Potential energy saving depends on climatic conditions, air ventilation rates, and typology of recuperators. In Italy, for example, they may range from 30% to 70% of the energy required for air renovation. Finally, let's consider efficient combustion with latent heat recovery. This is made possible through a condensing natural gas boiler which is able to recover latent heat from the flue gas. Cold water cools down the gas below its condensation temperature, so it releases latent heat that in standard boilers is wasted. Condensing boilers allow for an energy saving around 20% and require to be operated to relatively low temperatures of hot water between 40 and 50 degrees Celsius. This reduces the temperature gap between the heated room and the energy transfer fluid, achieving further saving due to the reduced thermal losses. In conclusion, other energy efficiency measures in HVAC are available. Correct insulation of pipes and ducts, inverter-controlled pumps and fans, intelligent energy management systems, occupancy and CO2 sensors, other advanced controls, low-temperature heating terminals such as radiant panels, low-energy coolers such as adiabatic cooling, desiccant dehumidification devices, compact heat storage devices, oriented people behavior, and many others for electricity end uses. Energy efficiency must be the main objective of the building and HVAC design for reducing primary energy consumption, investment costs, operation costs, and emissions.